Hello all, a very good afternoon. My name is Monica. I'm the host for this event. So first of all, I would like to welcome you all for the CADFEM technical webinar series. So today our webinar topic, fatigue assessment in ANSYS workbench with FKM and FKM Weld. So before going into webinar, I just want to give a crisp introduction about this. So a frequent challenge in finite element analysis is the evaluation of stress results, in particularly with cyclic stresses. So in this webinar, we will introduce you to the CADFEM ANSYS extension, that is FKM inside ANSYS. With FKM inside ANSYS, you can execute fatigue analysis according to FKM guidelines with the material database. So today our speaker is Mr. Florian Melander. He is working as a technology specialist for structures in CADFEM GmbH, and his areas of expertise is structural mechanics and fatigue. So I would like to hand over this webinar to Florian. So over to you, Mr. Florian.
Thanks for the introduction. So let's get directly started. As already promised, I want to show you a little bit what is the FKM guideline, and then also how to use the tools that were developed by EHF and CADFEM to help you to apply this guideline without much effort. As far as I was noticed, the meeting will be recorded, so we can have a look at that later on. And what the most important part is, when you have questions, simply use the text, the chat window to answer the questions, and we will try to answer them after the webinar. Some of them we will answer directly as far as time permits, and some we will answer later by email, but we will answer these questions. So let's get started. What we want to talk about is the FKM guideline. The FKM guideline is a short text documentary that could tell us what to do when our calculation is over. So I made my FEA calculation, I got stresses, I got strains, and what I know is my stresses are pulsating or they are alternating. What I don't know is, will my part withstand this? And in order to answer this most daring question, will my part survive? We need to take the stresses we get and assess them and say, okay, based on the experience, based on the guideline, that should work out. Good. The guideline itself is a modular structure. First, there's some general items, and in the general items, there are the limitations of this guideline. The FKM guideline is limited to steel and aluminium. So if we have different materials, we could use the proceeding, but we could not use the guideline directly because there would be no database behind it. So we could not be sure that every other material will behave like steel or like aluminium. And then the guideline is divided into two major sections. One is nominal stress approaches, which we won't focus today, and the other one is local stress. Local stress is the interesting part for us because we start with FEA, so what we get is the stress at a notch directly. And when we have the stress at a notch directly, we already have the local stresses. And what we then have is the local stress from the FEA, and what we have is the nominal values from our steel. So if I have an S235, I know the yield is at 235 megapascal. I know also the ultimate is at 370 megapascal. And if my stress is now at 200 megapascal, I know it will not yield. But I'm not sure if my stress is at 200 megapascal and it's a pulsating one. I'm not so sure if it will have an endurance, if we are below the endurance limit. So if I could survive this stress load indefinitely, or if we just have a certain amount of cycles left before my part will fail. Because of the guideline aims to support us with any kind of calculation, static, fatigue, welded, unwelded. We have reoccurring entries in all of the sections. So in nominal stress, I have a static stress approach. In local stress, I also assess the static strength. Nominal, I go for fatigue, and in local stress, I also do the fatigue calculation, and the equations are pretty similar. And for that reason, some of the pages are simply duplicates of other ones. That isn't really an issue because it makes the guideline so much more easy readable. What is the general concept? The general concept from the guideline is that we provide the stresses. We get the stresses from an FEA calculation. Usually that's what we do because we use ANSYS. We could also have the stresses by a hand calculation when we work with nominal stresses. And from the other hand, we have our material properties. And with material properties, I mean, I have my yield, I have my ultimate. And usually what we have is we have the yield and the ultimate for our sample. So I have a small sample, and we put our small sample on the testing rig. And what we then get is a value that is true for the small sample. What we have in reality is that our sample will be much more close to perfect than our real part. The sample will be polished. My real part might be polished. Usually it's not because it's too expensive. And also my real part might be much, much bigger than my small sample. And the point is, when I have a small sample, I can produce that really well. Especially when I make some kind of heat treatment. I can control the heat on a 1 centimeter part pretty accurately. If I would have a 1 meter part, so 1 meter in diameter, and I would heat that up so it will really be glowing, and I could try to cool it down, I will see that I no longer have the temperature control because this big chunk of metal won't be cooled down easily. So I only get the surface cool, and the core will still be awesome hot. So what we have is we have some material factors we calculate in to compare the sample we have to the real part we have. So my material properties will suffer a bit, but will be then closer to reality. Because we are closer to reality, we need some safety factors. Usually the material is not the big thing. The big thing is what happens with our loading, because we can tell the customer, hey, you need to be extremely careful with your loading. You only are allowed to use exactly this loading. Customers tend to do things sometimes a little bit different. So what we need is a safety factor to say, with our stresses and with our material properties, our part should withstand, and then we have a safety factor to ensure that it will really be okay. In the end, we get the assessment. We simply calculate that through. What is a little bit different in the FKM guideline is that we don't go out with a safety factor. What we do in the end is we get a degree of utilization. That's just a simple mind game. When we have our safety factor, and the safety factor is 1.1, because we know our part pretty well, and then we go it down, it goes up through the different department heads, who are all responsible that this part will survive at the customer side. Then the first one will say, okay, 1.1 is pretty critical, let's have 1.2. The next one will say, 1.2, I would like to see 1.5. And so with every instance that is checking if your part is designed right, with every instance you get more and more safety, and so your part gets getting bigger and bigger and bigger and heavier and heavier and heavier, and in the end it's just oversized. We wouldn't have even need that. And with the FKM, the point is I have the safety factor I need. I compare the stress I have to the stress I should have, reduced by the safety factor, and then I get 80% of the material is utilized. And when you tell an engineer 80% is utilized and 20% are irrelevant, he's trying to go, well, maybe we could get to 100%. Good. I want to show you how we could calculate that in ANSYS with the FKM inside ANSYS 2. And what we have here is a small example. It's a small gym bar, so for spotting exercises. And what we have done here is we have this connection part, which is casted. And what we're going to do is we want to use the FKM inside ANSYS tool by activating that on the project page. And I will leave the slides just to go for the live presentation. So, this is my part, fixed on the bolts with a point mass of 120 kilograms with standard Earth gravity. And so I get stresses, I get strains. And now I know I have a stress of 155 megapascal. I'm not really sure if that will be endured or if not. And for that reason, we use FKM inside ANSYS, which is an extension to the ANSYS module. And after we activate this expansion, we have this additional line here, where I can say, okay, I want a new FKM calculation. The first things first, I have to say, what do I want to calculate? I could go over all the parts and say, okay, make me an assessment for all the parts. I will now limit myself and just say, okay, I want to have a result for this body and this body. The selection is the same like it's always is in ANSYS. We could also go for surfaces. If our properties change from surface to surface, maybe I would say, okay, here's something critical. I polish the part here, and I will not polish the part anywhere else. Good. Then I've just said what I want to, where I want to calculate. Now we have to say what we want to calculate, and when we define our load cases, the tool will scan through our structure tree, look how many calculations do I have, how many load steps do they have. At the moment I just have one calculation with one load step, so I have to use this load step. And now he asks me, from this load step 1, what is the loading type? Is it static? Is it pulsating? Is it alternating? Is it manual? I wouldn't say it's static, because that would mean we have to hang on this gym bar for an indefinite period and we only can use it once. That's not really going to happen. Also, alternating, a complete reverse of the load doesn't make so much sense, because that would mean we have to hang on the gym bar and we have to push up the gym bar with our total weight. That's not the kind of thing we usually do. So it is pulsating. I have a load, I go down through the loading of 0, then I have a load again. We also could use a manual stress ratio, but in this case it's just a pulsating load. And the next step I have to say is, what do I want to calculate? Do I want to calculate that it's a fatigue limit, so whatever happens with the given loads, this part should never fail. Let's have a short let's have some thoughts about this. When we think about a gym bar, does it really need to be have a fatigue limit? So has it to endure everything on forever? What I just did is I said, okay, maybe someone is really training hard, really hard, and is training all 3 days for 100 repetitions and do that for 10 years. When we calculate that, that would only be 122,000 cycles. So not really endurance limit, which would be 2 million cycles. To be honest, I see that reality is more a reverse of the numbers. It's more all 100 days, 3 repetitions. That's more realistic. But let's go for someone who's more into sports than I am. And I could say not a fatigue limit. I want to have 120. Let's have 125,000 cycles. And with that, I do not assess it for eternal life. I just assess it for a life of 125,000 cycles. Good. The rest here are more or less tolerances. The guideline expects things to happen in a certain way. So what we expect is that our principal stresses are oriented so that one of the stresses is normal to the surface. That's usually the case when I have an unloaded surface or if I have a pressure on the surface. The only point where it's not like that is when I have a friction on the surface. Then it wouldn't be totally true that one of the principal stresses is normal to the surface, but usually that's true. And for the guideline, it's always absolutely true. And when we make that with an FEA calculation, we will see it's relatively true, not absolutely. So we need some tolerance here, and the tool automatically checks if we are above or below this tolerance. When we are above it, then he will say, okay, I will make an error message here, and when we are below, he will give us simply the result. Good. And then we have to define the major part. I have to define the local settings. And with the local settings, I have to say everything that can be evaluated primarily from the software itself. So, first things first, the material. I already have defined the material in ANSYS Workbench, but we decided that in the FKM tool I can change my material. The reason for that is pretty simple. When I have steel, I usually have a Young's modulus of 200,000 megapascal. Poisson's ratio is round about 0.3, and how much my yield or my ultimate is doesn't really matter. Not for the calculation. The stresses will be the same as long as I have a linear calculation. And we will have a linear calculation in the first one. And for my strength assessment, it is critically important what is my yield. So for the strength assessment, it is important if it's heat treated or not. And for that reason, we allow to change the material in the FKM assessment. So for the calculation FEA, to get the stresses, I could go for any steel because Young's modulus Poisson's ratios are the same, so the stresses will be the same. And after that, I can still decide I want this bit, this steel, or I want another steel. So I can also check if I build it with this material, will it be okay, and if I build it with this material, will it also be okay? So I can just make some variants very, very fast. There are a lot of materials already in the database from FKM. We also have the possibility to make our own materials based on very um, on very simple points. So what we could do is what we only need are three static values: yield, ultimate, and elongation at break. And with these three values and the material group, so what is it? Is it a steel? Is it an aluminium? What is it? We can estimate all of the properties. I want to have cast material, and because I want to have a cast material, I don't want to look that cast material out here from the list. I know it's somewhere in here, here around. What I directly can do is I can say, okay, first I want a cast material, and now I only get the list with my cast materials. That's just a short filter. Good. Then there are some questions we have to answer for our simulation. One is the effective diameter. The effective diameter is more or less a value, a characteristic length. It's more like the hydrodynamic diameter we know from fluid calculations. It don't necessarily have to be a diameter. Why it's in us to get the size effect? The bigger my part is, the more issues I have with constructability. So if I have a very small sample, I have top material properties. They are perfectly what they are supposed to be. When we have a little bit bigger materials, especially if they really got big, then we will run into troubles because our ultimate will no longer be 400, it might be only 360 or something like that. In order to put that into the equation, we need a characteristic length, and for the cylinder that's easy, that's just a diameter. If we have a sheet metal, it's the sheet thickness. If we have a pipe is nothing more than a sheet metal. It's just perfectly rounded. So we also have the thickness. And if we have something rectangular, then we have one side. Now what we also could have is we could have some more complex geometry, like we have here. And in this case, the equation is we take the volume and we multiply the volume by 4 and divide it by the surface. The concept behind that is that we say the more surface we have, the more easy is it to cool everything, and the better we have our process under control. In this case, that's round about 6 millimeter. The surface roughness is also not in the FAA model, but in my drawing, and that will be, in this case, 64 microns. Okay. And with 64 microns, the surface is not really good, but it is okay. And then we have the last one, that's the plastic notch factor. To explain the plastic notch factor, I made once a slide to see that. The basic concept is that when a part started to plastify, it is not necessarily failing already. So what we have here, for example, is I have a notch structure, and I simply put on some tension here. And when I put some tension, they started to plastify here. And now I have a material model that is linear elastic ideal plastic. So when it starts to plastify, when I have the yield, there will be no stress higher than yield. It will just plastify. And when I have this point and I pull more and more and more, I will come to the point where everything is plastified. And when I look at the force displacement curve, you see here it started to plastify, and it don't really affect the curve. And then I'm on the ideal plastic region, and so I get no more force. So after I have this force, it will simply fail. So I cannot get more load out of my structure than that. And for that reason, they say maximum load divided by the load where it just plastifies, the first point, that is my plastic notch factor. And I cannot directly say that's this way. What I could do is I could say in most cases that's equal to the notch factor, and the tool has a possibility to set that as the notch factor. Or I can say there is one value I test against. So I really calculate linear elastic ideal plastic, and I calculate either till the calculation is failing. I would not recommend that. Or I test till a value where I say, okay, that's the value I need, and I don't need any more. So in this case, I tested against the value of 2. So I calculated force where it plastified at the first point, increased the load by a factor of 2, and saw that my structure was still converging. So I don't know how much I could actually put on, but I could put on more than a factor of 2. Temperature will be room temperature. There will be no surface treatment. Now I can define what are the consequences of a failure. They are more or less low. And with this statement that I'm not really so afraid of failure, my safety factors are adapted. Good. Regular inspections, no, not really. Maximum load, yeah, that's probable. Set basic safety factors to 1. That is a special point where we just say we want to see if our degree of utilization is from our safety factors or from our part. So I won't use them now. Good. That is one body. The other is not set right now. They are exactly the same, so I just set them to the same value. What we also had was a check. Oh, the FAA and the FKM materials do not have exactly the same Young's modulus. I don't care much at this point because the difference will be very, very slight in the stress results, and so there will be slight in all the other results as well. Good. When I'm done, I can simply run the calculation, and an external solver will run. That was the black window we saw. And then I get my results. So I have a fatigue with 45% utilization, so it will be more than safely be assured. And I can look at my static and see also, or maybe not, 47%, so that will be also true. The good thing is I also can give out a report. If I have multiple FKM assessments, I can choose which one. I want that usually only for the critical node, not for every node. And what the system will give me then is a report with all my entries and, more important, for the critical node, with all the intermediate values that have to be calculated. So if someone is going to recheck my calculation and is just checking, is it okay with the FKM calculation, then he can refer to this report and check all of the values and the intermediate values. So we can simply print that out and give that as a final report for our assessment. Good. Then let's switch to the welded part. And when we have welds, there's basically one major issue, and the major issue is we cannot get the stresses here right at the beginning of the weld. There will always be a singularity, and a singularity has infinite stresses, and infinite stresses are hard to assess, other than to say, okay, it will fail, but not all of our parts will fail because of singularity. And for that reason, there are three basic concepts in FKM, but also in every other weld assessment. And the first one is nominal stress approach, where we just say, okay, we go for the stress, for the forces, not for the stresses, and then we calculate from the surfaces of our weld area, how much should the stress be with this cross section and with this force. The stress that comes out of that is pretty much virtual, but with these virtual stresses we could compare them to the corresponding classes, to the corresponding details, and with this comparison to the corresponding details, we can say, okay, we will have got this degree of utilization. The tool will help us in two ways. One is for shell elements, and for shell elements, it's a nominal stress approach, and this nominal stress approach is built to be fast. So what I can do is I have lots of seam welds. I can say I want to find them all. And what he is doing now, he's going through all the connections and say, okay, I have here my fan, I have my upper plate, and between these two it is welded. So I get all those connections. I could sort them, but in the moment I know they're pretty much all the same. So I can say, okay, you are from which material again? They are S355. The thickness is below 40. So I also get my material. I also could show the material properties. And now I have to decide, what are they? They are full penetration or back welded, because I want to have them with seam welds on both sides. The weld quality is not verified. Residual stresses are high. I haven't sorted them, so I don't give them a tag right now. What I could do is I could sort them with a tag first, and then only set them filtered by the tag. What he's asking me is the number of segments. I need that for having a straight line or a curved line. When I have a curved line, I couldn't use just one segment, I need more. We recommend to have at least 4 elements, 4 segments above 90 degrees. What a system is automatically trying to do is he's automatically trying to look, is that a curved line or is that a straight line? And when he sees, that's a curved line, he automatically switches the number of segments to more than 1. The default value is 3. Good. Now I could also go by, will there be plastic deformation allowed or not? If they would be allowed, I could set here for 1.2 in both according to the guideline. Later I can also go for the sections. For the sections, first to say what are they. This is now from one of the fans to one of the seam welds, and here I have the seam weld that will carry all the load. The other point is I have my ground plane, and the forces will not go over the weld, they will go in the sheet metal. So when I have my nominal stress, the reference should not be my seam weld, the reference should be the thickness of my sheet. So what I could do is I could say, okay, all of the sputtums, they are continuous sheets. Also all of the tabs, where I have exactly the same point. Also here the forces are not necessarily going into my seam weld and to the fan, they are within this top plate. So what I could do is I say also you are all continuous sheet. And my fans are all both-sided welds with a weld cross-section of 3 mm. The software will always assume the thickness is that and that, and when the thickness is that and that, then he will estimate a weld cross-section. And what I could also do now is I could change my details to another FAT class if it would be not a seam weld but a butt weld. Then I could go for 100 and not for 71. What we did is we preset the most common FAT classes. So in the most cases, I can use them first, make my first calculation, and then if there is anywhere trouble, I could go in back and look at this special seam weld to make that approach a little bit finer. When we look for the load case definitions, then we will see that is all we already had seen. I can do exactly the same things. I can go for fatigue limit, fatigue strength with a couple of cycles, and I could also say that is not only a fatigue strength with a number of cycles, but not all of the cycles are of the same amplitude. Some of them are lower. Good. In this case, I go for the fatigue limit. And what I get now is he will again calculate. And what he will do is he will give me for each segment one result. So I have 11%, 5. I have very small segment sweep right in front, and I have higher stresses here. So I have 44% degree of utilization in this foremost area. Good. What I could do for fatigue, I could also do for the static. And what we also could do is I could say, okay, I do not want to see maximum utilization. I want to know if that is a stress perpendicular or bending or shear, which of them is causing me the trouble, so I can also look what are these stresses. And here I see there's not really a normal stress perpendicular, so that is also the reason why we don't have much of a degree of utilization in this area. Simply just a nominal stress. Then there's a second concept, how we could approach seam welds, and that is a little bit more detailed. That came from the 60s, where we started to use strain gauges to measure. And what people tried is they said, okay, I can't measure at the seam weld directly, but I can measure in certain distances, and then I could estimate how large is the stress at my seam weld. And with this approach, I have again a stress where I can compare against my classes. Here the handling will be a little bit different. Here. I have my weld. In this case, I have a butt weld. Could also be a seam weld. I have my load conditions. In this case, I want one to be static and the other one to be alternating. And he will look for the worst combination of these two. I want to have a fatigue limit, and I want to calculate the static and the fatigue. And now I have to define my weld. Basically, there will be one type of weld, so I want one weld connection. I can say which is the material. Is it full penetration? In this case, I do not want to have a plastic multiplier. I can set my safety factors. I can set again my FAT classes. We again set the basic classes that are most likely. And now I can say, okay, there's a weld tip. And now I have to say, where are my starting lines? From where do I start with my calculation? Where do my paths start to go into my part? And I take these as selected. And these are the surfaces where the paths are to be mapped onto. Now he would know he has to draw paths from here into the surface. What he didn't know right now is how much is the distance. The distance is depending on the thickness of my sheets that are welded. Or if it's thicker than a sheet, I could simply switch to hard stop type B, then it would be a fixed distance. We try to make it an automatic way so that we don't have to enter the thickness. Unfortunately, that only worked in 95% of all cases. So we said, okay, before we make something wrong, we have to set the thickness. In this case, they are all 20, so I could do them all for 20. If there would be two sides, I could have also made one weld connection but two weld toes. So I could set one of them all to 20 and one of them all to 10. Good. And then I can now automatically generate the paths. So I just get my result. And now he will give me the results, the degree of utilization. In this case, I was a little bit too optimistic. So I'm right above the way I want it to be. I want to have no more than a degree of utilization of 100%. I'm now at 300%. So this part won't make it. When I leave the result for once and come back, then I also get my path points shown. So this is the distances where he gets stresses extrapolated to this point, and then assess them against the material we have. Good. There would be a last way how we could address seam welds, and that would be a modeling guideline where we use a 1 millimeter radius at the end of our seam welds. In the moment there is no support for that with FKM inside ANSYS because there's nothing we really need to do there. We just have this 1 millimeter radius, and we would compare this 1 millimeter radius to the FIT class 225, and that would be everything. So there's no need for it to assist us. That could change in the next years when highly loaded surfaces are coming into this approach, where we need additional information from the model that we could acquire automatically. Good. Then I'm open to your questions. You can simply write them into the chat, send them to everyone, then I will also see them. Good. There was a question to the effective diameter. The effective diameter is a characteristic length, I would like to tell it, where it's going to find something about what I can do and how to describe how large my part is. So when I look at this part, for example, there would be one characteristic length that really will describe my part. That would be the thickness of my sheet metal. That would be 20 millimeters in this case. When we now look at our part here, the tubes will have a thickness that will be easily to be assessed, because I could say, okay, that's nothing more than a sheet thickness. Same here. And this part is the thing that is a little bit out, because I have more or less a dominant thickness. So it's not that one part is really, really thick and another is really, really, small. And for structures like these, the guideline said, okay, we could take the volume, which would be 40,000 millimeters here, multiply that by 4, which would be 160,000, and compare that to the surface, which would be 31,000. So I would have 160,000 divided by 31,000, which should be around about 6. And then I have an estimate how this characteristic length could be. If we have a clear cross-section, it's more likely that we could directly have a characteristic length from this cross-section. But usually we go for this point, because our parts are simply too complex. Good. Then I get a lot of questions. So where is the theory for the welds? The theory is in 2 sources. One of the sources is the FKM guideline itself. The source here is pretty short. There is a couple of things in there, but not everything. The basic concept where the FKM guideline itself is referencing to is the guideline of the International Institute of Welding. And the International Institute of Welding made it pretty clear what is all there, so we can go there for reference. So everything should be in the EEV, in the International Institute of Welding. Good. The question was also, is there one ACT for shells and for solids? Yes. The structure stress concept is to be expected to be with solids in the moment and only with solids. And the nominal stress approach for welds is expected to be with shells. And the unwelded is to be expected with solids. Good. Good. The question is nominal stress approaches. When we use ANSYS, we get structural stresses, we get local stresses. What the software will do when we have here our point, it will take the stresses, the forces we have in this region, and with the forces in this region, he will calculate a nominal stress. So he will take the forces and moments from this elements between these two nodes, and we'll compare that to the rectangle where I have the basic information, and then we will have the nominal stress, and this nominal stress will be used in the assessment. What is the survival probability for fatigue? It will be 97.5%. That is a point the guideline simply says. When the degree of utilization is below 100%, it will survive. If it's above 100%, we will just no longer have the safety factors in there. They will not instantly fail, but we no longer have the safety factors the FKM wants to have. Where do we find material data? Usually we don't have to find them, because what we have is we have a pretty large database where a lot of them is in, and what we could do is I could define my own material, new steel, and all I have to do is I have to say what kind of material is that. That is a stainless steel, and it has an ultimate of 500 and a yield of 400, and yield and ultimate we will always have. And with these I get all necessary information I need for the assessment. Good. You will receive a copy of this presentation. And what is in the FKM inside ANSYS is all three modules we have seen here: welded, unwelded for solids, welded with shell elements for a nominal stress approach, welded for shell elements with structural stress approach, and what also is in there is a link to the material database from the IMA Dresden, which is a university of in Eastern Germany, and they have their own testing rigs and testing immensely for industry and also for university studies, and also for them is they included their own tool which we could also access with the FKM Inside ANSYS license.
Hello Florence, sorry to interrupt you. Could you see the questions from the participants on your screen?
I can see some of them that are coming to me. I am not sure if I see all of them, because it might be that some of them are directed to you, and I can't see that.
Actually, I can see many questions in my screen, so we can take some time to answer a few questions if you're comfortable.
Mm-hmm. Yep.
So once you're done, we'll start with question and answer session.
Good. Good. I see one more question that I have to address directly. When I'm with my when I'm with my shell models, how are my contacts to be expected?
Okay.
And that will be, I have different meanings to do that. Usually, I personally prefer that I have a continuous mesh, so that is an assembly. It could also be a mesh connection or a contact. So that will be all possible. Good. There's also a question, why is the overload case constant over R ratio, not over mean stress, but it's just constant over R ratio, not over mean stress, because I didn't change the settings. But you have all possible cases from the FKM guideline. Okay, that are most of the questions I can see here.
Okay, Florin. Actually, we're already out of time now. So what we can do is we can answer all these questions over mail to the participants. Is it fine?
Yeah, so you collect all the questions, send them to me, and I send them back to you with the answers.
Sure. And it will be done at the earliest. So can I conclude the webinar now? Hello, Florin. Can I conclude the webinar?
Yeah, sure.
Okay. Yeah. So thank you everyone for participating in this webinar. So as discussed, we'll send all your answers for the queries over mail, or if you have even more queries, you can directly write to marketing@cadfem.in. So we'll be very glad to answer your queries. And thank you very much, Florin, for your beautiful demonstration on FKM and its extensions. So everyone have a great day.
You're welcome. Have a good day.
Thank you very much.